Number 34. A high-pressure gas cylinder contains 50 liters of toxic gas at a pressure of 1.4 times 10 to the 7 newtons per meter squared and a temperature of 25 degrees Celsius. Its valve leaks after the cylinder is dropped. The cylinder is cooled to dry ice temperature, negative 78.5 degrees Celsius, to reduce the leak rate and pressure so that it can be safely repaired. Letter A. What is the final pressure in the tank, assuming a negligible amount of gas leaks while being cooled and that there is no phase change? All right. So basically, if you are understanding the nature of what they're telling us, the nature of the problem is such that we're beginning with some initial sets of conditions, and then there will be some final sets of conditions. Okay, they're telling us also some things are remaining constant. So when we have something like that, whenever we interpret that we have changing conditions, I want you to use the combined gas formula. PIVI over NI times TI will equal PFVF over NFTF. I made a general video about how this comes about. Take a look in the description below. There's a link. It's called the ideal gas law, right? So I derived this formula basically in that video. And don't be scared. I know I used the word derived and everyone's like, oh, I'm not going to watch that video. But take a look at it. I think it'll help. So what we now need to do is we now need to say, all right, so is anything remaining constant between the initial state and the final state for letter A? Well, they said that they assume that there really isn't much gas that's leaking out. So therefore the moles of gas remain the same. Okay. The volume of the container also. Now remember, the volume of the container, it's rigid. It's a gas cylinder, okay? So it's a rigid container. The volume then will not change. The volume of that container does not change. And remember, whatever gas is inside of this fills up the entire volume of the container, okay? So just keep that in mind. So they are the same. So basically what I'm left with now is that I'm left with that the initial pressure divided by the initial temperature will be equal to the final pressure divided by the final temperature. They're asking me for the final pressure, and therefore that's what I'm going to solve here for now, right? So just simply cross multiply the TF on over. So we get the initial pressure multiplied by the final temperature, and I don't know why I turned that into torque. Doesn't that T just look so much nicer? Divided by then the initial temperature. All right, so here is the formula. Now all we should need to do is basically plug in the values, right? Now another thing is that they don't tell us whether this pressure here is the absolute or the gauge pressure. They don't mention it. If they don't mention it, just assume that it is absolute pressure, okay? And again, I described the significance of that actually in the notes section, in the tips section on that general video. So let's plug in the initial pressure. It's 1.40 times 10 to the 7th, then multiplied by the final temperature. And, oh, they gave it to me in Celsius, right? So I just got to convert. So simply just add the 273 to it, okay? So that's what I'm going to do here. I'm going to do negative 78.5. All right, plus then the 273. That's the final temperature. And then divide it now by that initial temperature. And again, they told it to us in degrees Celsius, so you got to add the 275 to that. Okay, so same thing. This will be 25 then plus the 275. And lo and behold, we will get our answer. So 1.4 times 10 to the 7th, multiplied then by negative 78.5 plus the 273. Then divided by now 25 plus 273. Make sure it's in parentheses. So we get a value here of about 9.13, 9.1, or 9.14, I guess, times 10 to the 3, 6, right? Times 10 to the 6, times 10 to the 6 pascals. All right, so this would be the new pressure. So the pressure went from being about 14 million to now being about 9 million, okay, units of Pascal. Remember, Newton per square meter is the same thing as Pascal. So this would be the answer for letter A. All right, so let me just write this on up over here. Okay, now let's take a look at the next part of the problem. I'm just going to erase this work for now. Part B, what is the final pressure if 1/10 of the gas escapes? So again, we're still thinking about the combined gas law, PIVI divided by NITI will equal PFVF over NFTF. Now the thing is, the 1/10 of the gas escapes. So let's think about this, right? We want to find the final pressure in the tank. So what's the volume initially of the gas in the tank? What's the whole volume of the tank, right? That's 50 liters. What's the final volume then of the gas in the tank? Well, again, it's still the gas fills up the entire tank. So the final volume of that gas in the tank is still 50 liters. So that means that we can simply cancel the volumes. So now what we're left with is we're left with Pi over Ni times Ti is equal to Pf over Nf times Tf. Now they say, what is the final pressure? So I need to find final pressure, right? If 1/10 of the gas escapes. So what I realized though is I don't know the initial moles and I don't know the final moles. Actually, what I could do is I could calculate it if I wanted. All right, and then that could help me calculate the final. But what I'm going to do is I'm just going to create a ratio, and the units and the letters will cancel. You'll see. So basically, I can say here that the final mole value will be equal to 9/10 of the initial mole value, right? Of the initial mole value. Make sure that that makes sense. It says the final pressure if 1/10 of the gas escapes. Well, if you started with 10 things and 1/10 of this escaped, how many are left? 9, right? This is how many are left. In other words, 9/10 will be left of whatever you started with, okay? That's what this formula is telling you. So, that being the case now, what I can do is plug that in for NF, all right? I'm going to plug this on in for my final mole value. Now watch what that allows me to do. So then it's Pi over Ni times Ti is equal to Pf over 9/10 Ni times Tf. And look, lo and behold, the ends will cancel now. Okay? And now we can solve. Let's solve this for the final pressure. Let's see what we get. So remember, just basically bring what's in the denominator up into the numerator over here, and then that's it, and then you'll solve. Right, so the final pressure will be equal to then the initial pressure multiplied now by 9/10 times then your final temperature, all divided then by the initial temperature. And that's it. Just plug it on in. So this is 1.4 times 10 to the 7th multiplied then by 9/10 times then the final temperature, which again, it's just going to be this addition here. So let me just do that now. Negative 78.5 plus 273. So 194.5, okay? So this is 194.5. And then this whole thing is now then divided, whoops, one second. And then this whole thing is now divided by then the initial temperature. And again, you can do that on out. That should be 298. So let's just do the math. So this is 1.4 times 10 to the 7th times then 9 divided by 10 times 194.5. And then take that answer and divide it now by 298. We're going to get a value here of, and I'll write it over here, that the final pressure here is going to be 8.22 times 10 raised to the, what do we have here? We got that. That is, I'm sorry, 6, it looks like, right? Yeah, times 10 to the 6th pascals. Okay, now that should hopefully make sense. All right, the answer to part B should be less than that of part A. Why? Because in part A, I assume no gas had escaped. In part B, now I assume that some gas had escaped. So if some gas had escaped, the pressure now in the container should be lower. Okay? So that should make some intuitive sense. All right. Let's take a look now at, oh joy, right? Letter C. To what temperature must the tank be cooled to reduce the pressure to 1 atmosphere, assuming the gas does not change phase and that there is no leakage during cooling? So again, Pi Vi over Ni times Ti is equal to Pf Vf over T over, I could have written that first, but whatever, Nf times Tf. So we're saying the gas doesn't escape, right? So what does that mean? That means the moles don't change, okay? Also, the volume doesn't change as well. Remember, it's a rigid container. So now here we are left with now the Pi over Ti is equal to Pf over Tf. All right, now it says that what temperature, right? So we're trying to find the final temperature this time. Okay, so just solve this equation for the final temperature. Literally all you got to do, bring this on over here, this on over here, bring this on over there. You're simply doing a series of cross multiplications and voila. I mean, you're done. Okay, it's so simple, right? Such an easy way to do it. So here's your formula. Now what we got to do is we got to plug in the values, okay? So the final temperature here is going to be equal to the final pressure. But wait a minute, they told us it's going to be cooled and it reduces the pressure to 1 atmosphere. You cannot plug in atmospheres here, all right? If you're going to use your pressure down here in Pascal. So just, you know, 1 atmosphere is now 1.013 times 10 to the 5th Pascal. These are equivalent, all right? Times by the initial temperature, again, it's going to be then the 298, as we found before, divided then by the initial pressure, which was 1.4 times 10 to the 7th. And lo and behold, here we will find our final temperature, and this should be 1.013 times 10 to the 5th times 298 divided by 1.4 times 10 to the 7th. And we get about, what? Wait a minute, what? I get about 2.15. Or 2.16. Right. Is that even, let me just double check my math, okay? I think, actually, as I'm looking at it, it kind of looks right, but I think that might, let me just double check because it's such a strange temperature in Kelvin. I mean, that's basically, it has no temperature to it. So 1.013 times 10 to the 5th multiplied by 298 divided by 1.4 times 10 to the 7th. Yeah, okay. All right, so that is the final temperature, all right? Yeah. Okay, that's the final temperature given the conditions that we saw. All right, so here's letter C. I'm going to take it over here. And that's the answer to letter C. And now, last but not least, let's say D. Does cooling the tank appear to be a practical solution? No. All right, no. This is basically close to 0 degree Kelvin, meaning that's like absolute zero. That's as cold, you can't get any colder than that. All right, I don't know how to explain how cold this is. I don't even know if we can, I don't even know if we can obtain temperatures this cold on Earth, even in a scientific setting. We might be able to. I think we have reached it on Earth in a laboratory setting, but yeah, no, it's definitely not a very practical solution here. I don't even know how to really relate this to something. I mean, if you were to think, you go out on a cold day, right? A cold day might be 0 degrees Celsius, right? That means that's 273 Kelvin, okay? That's on a cold day, right? Look at how much different. It's really cold, okay, guys? So anyway, thanks for tuning in. Appreciate it very much. Hopefully this helped. Please remember to help us out and subscribe, all right? Please, please, please. Please, take care.